Hello, I'm Mr. Malo, your online math teacher, and welcome to my channel. Today we're going to be continuing my series on analyzing functions from a pre-calculus perspective, and I hope that you're going to find this video helpful, and if you do, please consider smashing the like button, subscribing, and checking out my other videos. So, let's get going. Today in particular, we're going to be talking about even and odd functions. Now, this is a special property that function have, and it brings us to the question first: what does it mean to be symmetric, and what types of symmetries are there? So if you're like me, when you were a younger child, you would draw pictures and you would be drawn to the idea of trying to make my picture symmetric about a line. I draw a line in the middle of the paper, and I try to make sure my picture on the right of that line mirrored my picture on the left. And that's one of the types of symmetry we care about in math, and that's called linear symmetry. Another type of symmetry that we sometimes care about is called point or rotational symmetry. So that's kind of, think about as flipping over multiple lines or turning something. Now, we have two types of symmetries that we're interested in, this even and odd today. The first one is even, the second one is odd, and we say that a real valued function, and this works for complex valued functions if you know those two, is a function that's said to be even if f of x is equal to f of negative x for all x in the domain of f. All that says is if instead of putting in x, you put in negative x, you'll get out all the same values as if you didn't put in the negative at all. So, and this is an example of linear symmetry. An odd function is a real valued function that f of negative x is equal to negative f of x for all x in the domain of f. And this is an example of point symmetry. And you're going to have two different approaches to thinking about even and odd functions. You can either think about them algebraically, or you can think about them graphically. So we're going to start algebraically. And here's kind of my tips for doing this. Always start with even. It's easier. And you need to work for even to check odd. So even, you're just going to replace x with negative x in your function and simplify to see if it's the same thing as what you started with. So in a problem like A here, I'm going to do just that. I'm going to ask, what is f of negative x? So every x is being replaced by negative x plus 2 negative x to the fourth minus 8. And notice I'm using parentheses. Very liberally use parentheses when you're doing these problems. Simple algebra mistakes by dropping the parentheses and not raising something to the right power or not distributing something is one of the most common ways people make mistakes on these. So, and when I do this, my absolute value sign takes care of that negative there. My negative is raised to a fourth power. So whenever you have a negative raised to an even power, that means it kind of effectively kills off the negative. So that goes away. So it's really just x to the fourth minus 8. And this is equal to f of x. So what we conclude, we see f of x is equal to f of negative x, meaning f of x is even. So I have proved it, and I'm concluding f is even. Now, it turns out that the only function that's both even and odd is the zero function. But I require my students to prove that it's not odd also, because it gets them more practice. Now, if they can prove to me that 0 is the only function that satisfies that, then I'd let them get away with this, but no one's proved it to me yet. So now what I do is I look at f of negative f of x, and that is equal to negative. So again, parentheses, use them liberally. negative 3x plus 2x to the fourth minus 8. You can distribute your negative. That first term becomes 3 minus 2x to the fourth plus 8. And it's pretty clear that this is not equal to f of negative x, which we just found over on the left. So since negative f of x is not equal to f of negative x, then f is not odd. So again, I've made my conclusion too. So I proved it, I made my conclusion. So why don't you try doing G for a second? Pause this video, try doing G. Okay? Hopefully you paused the video and tried doing G. And if you did, you should have started with even and gotten the following. You should have shown your work here to see that this function, when I replace x with a negative x, is definitely not that same as that function g that I started with. So then you can conclude that it's not an even function. After that, you hopefully came up with this work. So when I do negative g of x, I end up getting the same function I got over here when I replaced x with negative x on the even side. So since negative g of x is equal to g of negative x, then g is odd. So here's an example of why I say always check even first, because you can use that work in checking odd. So don't just go straight for odd. So like I said, the only function that's both even and odd is a zero function, but I make people prove it if they want to use that, and no one's done it yet. But just do keep in mind, most functions are neither even nor odd. So if you get neither, that's not a bad thing. Most things aren't that. So this is how you can check it algebraically. The other approach is to tell graphically. And graphically, the way you're going to do that is say a function is going to be even if you reflect it over the y-axis and it lands on itself. And that makes sense based on our reflection rules. A function's odd if you reflect the graph over the y-axis and x-axis and it lands on itself. So this again makes sense because of our reflection rules. You can go check out transformation of functions to understand that. So with that in mind, there's two functions you definitely want to keep in mind when you're thinking of even and odd functions. And they are the following. The function f of x equal to x squared is even, so that nice parabola. And it's that way because if I reflect it over the y-axis, it's going to land on top of itself. Now, this should be your prototypical even example. What you want in your mind for an odd function is if it reflects over the y and x-axis, lands on itself, and the function x cubed does just this. If I reflect this over the y and then the x-axis, I'm just going to land on top of that graph. So these are the two examples you can keep in mind, because if you get something that's a little bit more funky, just remember these reflections are pretty easy to visualize, to ask, is this odd, is this even, really quickly. So that's your example of odd. But remember, most functions are neither. An example, and I'm just going to draw in the middle here, a square root function. This is going to be neither. If you reflect it over the y-axis, there's nothing over there to land on. And again, still, if you then reflect it further over the x-axis, there's still nothing to land on. Most functions fall in the neither category. So that's square root of x. You can think about that there as your example of neither, but most things are going to fall there. And that's really all you need to know for graphing them. It's pretty straightforward. So my tips are, keep those two functions in mind for even and odd. X squared is even, x cubed is odd. And when you're proving even and odd algebraically, just make sure to make liberal use of parentheses to emphasize what's going to distribute, what's being raised to each power, etc. Because algebra mistakes are the easiest way to not get those problems right. So I hope you found this video helpful. If you did, hit the like button, check out my other videos, and have an awesome day.